Yes, any questions in the break? Any questions did you come up with during the break time?
Hour'da hocam, pardon ben biraz önce sordum. İkinci sorunun şöyle, birinci bir kısmını değişik hocam sınıfta sorduğumuz vermişim. Definition olduğu yani gösterebilecek herhangi bir şey bulamadım.
Well, you see, the question is, we know the definition in terms of operators. Show that exactly the same definition, in a sense, holds for the matrices. That's what you need to show. Okay, so finally, after 1 month, we are kind of leaving behind the Stern-Gerlach experiment. But it was a good exercise. Since the Stern-Gerlach experiment, the states are quite simple. We only have a two-state system. It's either plus or minus. But of course, we are interested in more than just in which direction a given silver atom will split in a Stern-Gerlach experiment. We would like to describe more general systems. And if you are, one of the typical things that we measure in experiments is things like position, for example, or momentum. Those are the things that we measure. And these things are continuous. They don't take discrete values. So that is the first thing. What will change if our spectra is continuous rather than discrete? Well, one thing that we need to change is, for example, in our derivations, in the discrete case, we quite often use this fact. Or let's say AI Kronecker delta Ij is just Aj. J meaning the eigen representing the eigenvalue, eigenket, etc., which are discrete. So the sum is a discrete, the sum of I. Now, when we have a continuous spectrum, we cannot just use an index I, because usually notationally, the index I, J, K, L, M, they are used to denote quantities that change continuously, that change discretely, so you can just count them 1, 2, 3. And in the continuous spectrum case, it changes continuously, not discretely. So we will call them, we call them functions, basically. So our function is nothing but an expression of this form. Well, AI, you can just treat this as a function, in fact. You give me I will give you a number, which is AI. So this AI, in a sense, is a function from some discrete numbers to, well, in this case, to complex numbers. So you give me some discrete number, that AI gives you a complex number. Well, in the continuous case, we use different notation for functions. Rather than calling a subindex I, we call them let's call our continuous variable psi. Well, we cannot sum over continuous variables, but we can integrate over continuous variables. And instead of that delta function, we just need to use some other quantity. So this is what we want. So wherever we had a Kronecker delta in the continuous case, we now have a Dirac delta. And wherever we had a summation, now we have an integration. And to see that we should really map Kronecker delta Ij to a Dirac delta, you can also make some other argument. Well, this is equal to, let's just assume that I takes integer values. Or, I doesn't even need to be integer values, or just I takes discrete values, not necessarily integer. Delta I, AI, Kronecker delta Ij over delta I. This delta I is nothing but the separation between our eigenvalues. Well, when we are going to the continuous spectrum, basically this delta I goes to 0. Well, we have, in a given interval at least, we have infinitely many eigenvalues. So the summation over the eigenvalues of the separation of the eigenvalues times something in the limit delta I goes to 0, this is nothing but the Riemann definition of the integral. So this whole thing becomes an integral as delta I goes to 0. We have an integral of, let's say, di. Instead of I, just to be consistent with the notation, I just change this integration variable to psi of ai times some function. This function should be 0 for every two distinct numbers, I and j. If I and j are different, this should be 0. And it should be infinite because of this divided by delta I. It should be infinite when I and j are equal. Well, that is basically one of the properties of the Dirac delta. So that's why we have I minus j. Now this Kronecker delta just becomes a Dirac delta in the continuous case, basically because we are converting the summation into an integration. So that is one thing you have to pay attention to when we are working with continuous spectra. Well, you see, I'm taking the limit when these delta I goes to 0. That's the case I'm interested in, the continuous spectra. Well, when I take delta I goes to 0, first of all, this summation over here is the definition of the integral. So that's why it is converted into an integral. ai, whatever it can stay as it is. Of course, this is not the common notation we use for functions of a continuous variable, so that's why I changed it over here. And here I have another function. Well, this function, the properties of this function are, let's say, if I am talking about two different eigenvalues, this function is 0 in the limit as delta I goes to 0. If I am talking about the same eigenvalue or eigenkets, if I and j are equal, this is just 1. So 1 over delta I goes to 0, so it becomes infinite. So in that limit, this quantity is 0 if I'm talking about different kets, and infinite if I'm talking about the same ket, same I and j. Well, it is one of the properties of the Dirac delta. Now, another property of this function is, forget about this one. Forget about this ai. If there is no ai over here, this summation is 1. It should also stay 1 in the continuous spectral limit. So this function, whatever it becomes in the continuous limit, it has the same property as the Dirac delta in that it is 0 almost everywhere except at only one point. And it has to have one more property that, forget about this ai, its integral over I should be 1. That is the other property of the Dirac delta. Well, Dirac delta is defined by having these two properties. That it is 0 almost everywhere except at one point, and its integral is 1. That is the definition of our Dirac delta. So this function satisfies all the defining properties of the Dirac delta, so it has to be a Dirac delta function. So basically, this is the only thing you need to pay attention to when you are going to the, whatever we had derived before holds exactly the same over here. Just convert summations into integrations, Kronecker deltas into Dirac deltas. So basically, this becomes ai, aj. This just becomes psi I, psi prime. This is equal. This was Kronecker delta ij. Now psi prime inner product just becomes Dirac delta psi minus psi prime. And sum over ai, this was equal to 1. Now in the continuous case, it is the integral over psi of psi is equal to 1. Any questions on these?
İntegralin içerisinde graf notasyonu gösterebilir miyiz?
Sure, why not? For example, if you have any alpha, any ket alpha, this I can write as the xi alpha. The integral over all possible values of xi. Later on, when we will be studying the position space kets, then this will just become the wave function that you are probably more familiar with. So let's study position kets. Well, basically, we have the position is an observable. So we define there's an operator corresponding to position. Well, I will use this notation. In your book, it doesn't use this hat notation, but I will, as much as possible, I will use this hat notation to denote the operators, if there is any possibility of confusion between the operator and its eigenvalues. So when I act on it on some ket, it has eigenvalues. So xi is the position eigenket, and the corresponding number xi is the corresponding eigenvalue. So this is my position ket. Or, well, maybe if I use x, it would be better. Well, I can do the same thing for the y and the z coordinates also. And of course, x, y, when we are measuring the positions of particles, as far as the experiment tells us, we seem to be able to measure all of them as precise as we want. So we basically talk about x, y, z kets. So when I act on this ket with the x operator, I get the x, y, z. When I act on it with the y operator, I get y, x, y, z. When I act on it with the z operator, it will be z, x, y, z. They are complete. dx, dy, dz, all from minus infinity to infinity. X, y, z. This is equal to 1. So I can write any ket in terms of these. Let me write this shorthand notation, d cubed x. It's integral over dx, dy, dz. And let me use this shorthand notation for the position kets. So these are just some numbers, and these are my position kets. Well, as far as we know, yes. Well, this assumption, let's say, there are limits on this. So this assumption basically tells us that x and y operators, they commute. Okay, so just a word of warning on notation. Okay, I will be using this hat notation to denote the operators, but I am also using this hat notation to denote the unit vectors. So if it gets confusing, just make sure that you ask. So here, these are not the unit vectors. These are my operators. Similarly here, these are my operators. Well, do we really know that they commute? Well, we don't, to be honest. We have measurements, limitations on this. And most probably, at least at the what's called the Planck length, something like 10 to the power minus 30 meters, or even smaller, they do not seem to be commuting. We have theories at least claiming that they need not be commuting at that scale. So, and that is a whole branch of non-commutativity. In fact, we do have one system, which we don't need to go to the Planck scale, where we have this non-commutativity. But to discuss that, let's start with translation operator. Let's look at the translation, what we mean by translation. So because the commutation of the x, y, and z will eventually come, well, we will discuss it later on. In fact, let me not jump. Let me, before the translation of position, let me look at the measurements. I mean, in the case of the Stern-Gerlach experiment, it was kind of easy. We could measure with the spin whether it was up or down. There was only two possibilities. So we could definitely say that it's going up or it's definitely going down. But now when we have these continuous variables, continuous observables, well, you don't make so precise measurements. All the measurements have their error bars. So when you measure the x component, let's say, you say that it is between x plus delta x over 2 and x minus delta x over 2. So you start with this ket, let's say alpha, which we can write as in one dimension. Let's say for simplicity, this is the x alpha. Then you make a measurement of the x position. This is from 0 to minus infinity to infinity. Between, let's say, x0 minus delta x over 2 and x0 plus delta x over 2. So this is basically what we have. So we make a measurement of the position, and we find that the position of the object is between these values. So how do you make the measurement? Well, one way you can make this measurement is, for example, if you are using a digital camera, besides other things, it measures the position of the photons. So each pixel in your digital camera, it either says 0 or 1, whether there is a photon in it or not. But the pixel has a finite size. So the only thing you can do is you can say that there was a photon between these ranges within the size of your pixel. Of course, your digital camera also kind of makes some frequency analysis, but in the simplest black and white picture, let's say, each pixel will say that whether there was a photon in it or not. Well, that is a measurement of the position of the photon. But since the size of the pixel is finite, it's not point-like, so there's an uncertainty in the position. But after this measurement, if you make a measurement of the position of something, you know that its state will collapse. So we started with alpha, and after measurement, after collapse, the state will just become x0 minus delta x over 2 to x0 plus delta x over 2 dx x alpha. Of course, in saying this, we are assuming that it didn't really change the state except then causing it to collapse. So this is now the new position. Now the probability that the state is in the interval x0 minus dx over 2 and x0 plus dx over 2 is, well, in the discrete case, the probability was just the amplitude squared. But now we also have dx. Well, basically, since we have a continuous spectrum, there are infinitely many possibilities. One outcome, the probability of one outcome will basically be 0. the probability of the outcome to be within an interval, that is what will be non-zero. So in this continuous spectrum case, we cannot really talk about the probability, well, we can talk about the probabilities, but what will be important will be the probability density. And this amplitude squared is now the probability density we have. And if you integrate it over an interval, well, you see, this is dx alpha x alpha, which is equal to alpha dx x alpha. This is the identity operator. This is alpha alpha. This is just 1. So the total probability, but if we interpret this amplitude squared as the probability density, its integral is 1, as it should be, that the total probability is 1. So if the probability that this object is within a given interval is nothing but the density multiplied by the interval, or if it is an infinitesimal interval. If it's a finite interval, then you have to integrate this over. So let's say the probability is between x0 and x1 is, let's say, probability of this interval. This is equal to the integral from x0 to x1 of alpha x squared. Well, x1 larger than x0. So this will be our probability interpretation in the case of the discrete continuous spectrum. In the case of the discrete spectrum, the coefficients squared gave us the probability. In the case of the continuous spectrum, the coefficient squares gives us the probability density, whose integral gives us the probabilities.
Sadece dx elementi o zaman bizim aradaki bağlantıyı veriyor. Yani küçülttüğümüz zaman o direkt discrete'deki şeyi bağlayacak bizim için. Probability'yle aynı yere bağlayacak.
In essence, well, you see, how did we go from continuous to discrete? We just replace summations with integrations. Well, if you replace integration with summations, that should give us our discrete case. And if you are talking about in the discrete case, you can talk about one eigenvalue. So there's no integration, there's just summation. There's just one, that summation actually involves a single term, and hence it becomes probability in the discrete case. Questions? Yes.
Hocam, bir elektronun bir yerde bulunma çok continuous değil mi? Discrete modelde.
Well, you see, the position in general is not a discrete quantity. The electron can be found anywhere. You can talk about the probabilities of electron being in any volume. So there's no discreteness over there.
Ama bir şeyleri yok mu?
Well, we will eventually study them, but you see, when you see this graph, for example, a hydrogen atom in, let's say, I think it was 1p state. So this is usually how it is plotted. I think this was 1p. Okay, this is one of the orbital diagrams that you see. What this means is that, well, this doesn't tell me that the electron can only be found in these places. It only tells me that the probability that the electron is within this volume is 90%. Well, it depends on the convention. I think it was 90%. The electron can still be found outside. There's no limitation on that. The electron can be found here, here, here, here, but its probability will be smaller. With 90% probability, it will be within the volume bounded by the surface that you see.
Bir elektron enerjisi yani yakınlık ve uzaklığına göre değişen mi?
Well, you see, the energy of the electron, classically speaking, it depends on the distance from the center, but it also depends on its kinetic energy. So it's kinetic plus the potential.
Peki o zaman elektronun kinetik enerjisi nasıl diskrit oluyor?
Well, you see, even in classical physics, the electron can be found anywhere. Of course, given an orbit, there is a single trajectory, which, by the way, assumes that you know the position and momentum of the electron at every point. In quantum mechanics, it doesn't happen. So you cannot really talk about, okay, the electron is at this point with this momentum. You cannot even talk about that thing. So you cannot really relate the position and energy. You cannot really talk about the position of the electron and the energy of the electron, because they are incompatible observables. If you say that, okay, the electron is over here, then you cannot talk about the energy. As I said, they are incompatible observables. If I want to talk about the energy, I shouldn't be measuring its position. So although it seems that there seems to be some, let's say, inconsistency, because if I'm not understanding you wrong, if the electron can be anywhere, its energy can be anything, not discrete. But if you are talking about the position, you cannot talk about the energy. If you are talking about the energy, you cannot talk about the position. You can only talk about probabilities. That is something new in quantum physics. That doesn't exist in classical physics.
Sanırım algı olarak hep sanki aynı harmonik hareketi yaptığı için bir yere bağlı gibi düşünüyoruz. Aklımıza hata
Well, you see, in interpreting these, we will hopefully discuss this towards the end of the semester. In interpreting these orbital diagrams, don't think them as exact positions or the trajectories. These are not trajectories. These are just some mathematical surfaces. They're not even physical surfaces, which bounds the volume. And the definition of that volume is that the probability that the electron is within that volume with such and such a probability. Well, this volume, the surface is, I mean, if I'm not wrong, the surface is chosen such that at every point on the surface, the wave function has exactly the same value. That is one constraint on the surface. And that value is chosen by the constraint that the probability that the electron is within that volume is such and such. And the way to calculate the probability within the volume is just take the wave function squared integrated over that volume. That is how we come up with those orbital diagrams. They are not trajectories. They don't tell us that the electron is definitely on those surfaces, or they don't tell us that the electron is definitely within that volume. Most probably, the electrons are within that volume.
Peki bu diagram vardı hocam. Direkt oturup probability üzerine mi diyor, yoksa bu volümün içerisindeki her noktada mesela probability density birbirine eşit mi? Hayır.
No. On the surface, yes. Inside, no. Okay, that I will leave aside for our discussions on the hydrogen atom. Now let's continue with our case of the position. Now one important thing for us will be the translation. Now, first of all, what we mean by a translation. Let me define the sket x0. I will define it to be the state of a system that is localized around, let's say, x0. That's how I define it. I mean, it's not the position. It doesn't have to be a position eigenket. But I'm just saying that, okay, let's just take this kit. It might have some distribution in position, but that distribution is kind of localized around one point. So let's say if this is x0, I can have this probability distribution, a Gaussian probability distribution, for example. Then a translation of this one, well, let me use the t. A translation by, let's say, dx will be just this another kit which is localized around x0 plus dx. This is the definition of this translation. This is what I call a translation. Now, this is a translation in the x direction. Now, what else do I know about this translation operator? What else I can say? Let's say I have this x0. I translate it by, let's say, delta 1 first. Then I translate it by delta 2 next. This will be equal to translation by delta 2 of x0 plus delta 1, which is x0 plus delta 1 plus delta 2. But this is nothing but translation by delta 1 plus delta 2. In fact, this should be true for any x0. So, and this kind of tells me that translation satisfies this property. Now, what else do I know? I know that x0 plus delta 1, well, if I'm just shifting it, the total probability shouldn't be changing. So this shifted state should have the inner product 1. Now, the probability distribution will change. The probability distribution does change, so it is shifted. But the total probability that the particle is somewhere doesn't change. Before its shift, it was most probably over here, but it was definitely somewhere. After the shift, it's most probably over here, but it is definitely somewhere. But this tells me that x0, t delta 1 dagger, t delta 1, x0 should be equal to 1, again, whatever x0 is. But for this to be true, t delta 1 dagger, t delta 1, this should be the unit operator, which basically tells me that t of delta 1 is a unitary operator. Well, what else do we know? T of, let's say, minus delta 1, T of delta 1 is T of minus delta 1 plus delta 1, T of 0. Well, T of 0 acting on x0 is just x0, no shift for any x0. Well, this tells me that T of 0 should be the identity operator. Well, if I combine this with this result over here and this one, I can see that T of delta 1 dagger should be equal to T of minus delta 1. So these are all the properties of the translation operator. Well, we have this new operator, the translation operator. We have the position operator. So let's see, how do they influence each other? Let's see, translation by delta 1, x, acting on this. Now this time, let me use a position eigenket. This is a position eigenket. Before I defined x0 state as not necessarily a position eigenket, but now let me choose a position eigenket. This is equal to translation by delta 1, x multiplied with the ket x. This is equal to, well, this x over here is a number. It's not an operator. This is equal to x times t delta 1 x, or this operator, this is nothing but x times x plus delta 1. Now let me look at the other way around. Not in this order, let me change their order. X hat t delta 1 acting on x. This is x hat x plus delta 1, but this is x plus delta 1, x plus delta 1. So what can I say? T delta 1 x hat minus x hat t delta 1. That is their commutator. Acting on any position eigenket is actually just delta 1 x plus delta 1. Or t of delta 1, well, let me rewrite it in a different form. This is equal to delta 1 t delta 1 of x plus x. This should be true for any ket x. Well, x form a base, these kets form a basis. So if this identity holds for any basis ket, it should hold for the operators. So the commutator of t delta 1 with the x operator should be equal to delta 1 times t. So this translation operator should also satisfy this property. Yeah, I mean, this is the translation in the x direction I'm talking about, and I'm taking the commutator with the x in the x direction. Now, I didn't yet say anything about momentum. This is just position. I'm talking about position translations. I'm talking about the position operator. Now, let's remember some of the properties of t that we had derived. T of 0 is 1. Now, t of delta, well, I can just treat it as a function of delta. I can just consider a Taylor expansion. Well, the Taylor expansion will have, let's say, t of 0 plus delta times the derivative of t of delta with respect to delta, evaluate that delta is equal to 0, plus maybe some other terms. I will, just for simplicity, I will just consider very small delta so I can neglect the higher order terms. Now this is 1, t of 0. I will give this a different name. This is just some constant. It doesn't depend on delta because I'm evaluating this derivative at delta is equal to 1. Delta is equal to 0. There's no delta dependence left. So I will just call that plus I k delta plus, there are terms that I ignored. Those are proportional to delta squared or higher order terms. So what can I say about this delta, this k? First of all, t of delta dagger, t of delta, this should be equal to 1. Well, so 1 plus I k delta dagger, 1 plus I k delta, this should be equal to 1 plus some possible terms that are proportional to delta squared. Well, let me just open up the product. This is 1 minus I k dagger. Delta is a real number. It's just a position, just like 1 meter, 0.3 centimeters. Delta is a real number. 1 plus I k delta should be equal to 1. Well, 1 plus I k delta minus I k dagger delta plus some terms of the order of delta squared. Well, I'm just ignoring this product, which is of the order of delta squared. This should be equal to 1 plus some corrections of the order of delta squared. Well, you see, this one cancels this one over here. Up to delta squared, terms of the order of delta squared, this should be 0. K is Hermitian. So nice, it can be an observable. It might correspond to some observable because we know that Hermitian operators, they correspond to some observables. So what else do we know about this K? Oops. Okay. We know this property. So 1 plus I k delta commutator with x hat should be equal to delta plus some corrections of the order of delta squared. Well, you see, this t is 1 plus some term proportional to delta, but that is some term of the order of delta squared. Well, let's look at the left-hand side. This is the 1 commutator with x plus I delta is a number, I can just take it out. K commutator with x. This is equal to delta plus something of the order of delta squared. Well, this is just 0. I can cancel these deltas. So here I get 1. Now I can take the limit that delta is exactly equal to 0. Well, if I take that limit, I obtain k commutator with x should be equal to minus I. So k, which we will discuss it on Wednesday in more detail, k which generates translations in the x direction is an operator. That operator, its commutator with the position operator is just minus I. It's a Hermitian operator, that k. So what is that operator? That we will discuss on Wednesday. So you will probably say that, oh, it's the momentum. How do we know? Okay. Any questions? Any last questions?
Pozisyonla translasyonun komutası bana ilginç geldi. Ben komutası. Çünkü eğer pozisyonu açabiliyorsam, translate ettiği zaman da açabiliyorum.
And you will get a different answer. That is basically what it means that they do not commute. The position that you measure after translation is different than the position that you will measure before translation. So this non-commutativity basically means that. And also keep in mind, K is not the translation operator. K generates, or we can define the translation operator in terms of K but K is not the translation operator. And as you said, the translation operator does not commute with the position operator, which basically means that, this commutator, in a sense, it corresponds to making two measurements, but in different orders. Do they differ? If they differ, then the commutator is non-zero. Another problem, translation operator, by the way, doesn't correspond to a measurement because it's not Hermitian. It's unitary, but not Hermitian in general. For certain special values, it might be Hermitian, but in general, it's not Hermitian. It's unitary. Okay, so see you on Wednesday. Your homeworks, okay, the next homework will be for next Monday. That one, well, that is your third homework, not your second homework. The question I wrote, it is for your next homework, not this one. You will not hand that in for this Monday, for next Monday, sorry.